All right, so we're on the third video as an introduction to electricity and magnetism and applying it in circuits. We're laying conceptual foundation so that then you can get into the mathematical stuff and keep the meaning in mind. Again, it's pretty abstract, but you can see stuff and it clearly works around us, which are light switches. So to get mathematical with this, we've got to talk about how much. Talk about what electric charge is, in a sense, even though we haven't said why does an electron have electric charge, why does a proton, but we talked about why atoms do. And we're just going to stop with that. We know that they can pull and attract and repel. So we want to talk about how much. So how much electric charge, again, the symbol for electric charge usually is a lowercase q or an uppercase q, either way. It depends, and there's not really a hard and fast rule there. There's two units that are common. There's a tiny, tiny unit, which is called the fundamental unit of charge, or E. Looks like electron, right? But it's not just electron, so it's just E, electric charge. And then there's a huge unit called the coulomb, and you'll learn coulombs a lot later, soon. And that's capital C, capital C. Again, be picky with your notation. We got to know what you're talking about. You can't make up your own. How tiny is an E? One fundamental unit, one E, is 1.6 times 10 to the negative 19 coulombs. Remember that number. That should be something you just know. 1.6 times 10 to the negative 19 coulombs. It's a tiny number. So that means 1 coulomb is how many E's? Well, how do you do that? Again, make sure you're doing this on paper or else you won't develop the skill. You just solve for 1 here, so you divide by that. So that would be 1 over 1.6 times 10 to the negative 19 E's, right? 1 divided by that. And what that gives you is 6.25 times 10 to the 18. That's 10 to the 9 times 10 to the 9. Or a billion billion. So that's a lot. That's a big number. Now, as a reference and something to think about and put to the side, you might have heard of Avogadro's number. If you take chemistry, you will, and as you go on in physics, you will too. And that is 6.02 and so on times 10 to the 23. We use that to talk about how many atoms, how many molecules, how many this and that. So, so there's sort of a connection there, and we'll see. But a coulomb is generally a large unit of charge, and if you've got something that has a net charge of a coulomb, it's dangerous. And so it's good to have a sense of this. We'll talk about that. Okay, so that's it. Those are just two units that we use to say how much electric charge. We've come a long way from Ben Franklin, right? And that's the same attracting and repelling. So atoms. You may have heard of this. Neutral atoms, which is common. You and I are neutral, so we're not electrically attracted or repulsed unless we drag our feet across the carpet and we touch each other and shock each other a little bit. But for the most part, things are neutral, and so the number of electrons equals the number of protons. A positive ion, the number of electrons would be more than or less than. So that's when an atom gets its charge by losing electrons, and the net atom is positive ion, is the term. To be a negative ion, to be a negative ion, you've got to have more electrons than protons. More electrons. And that can happen. But this is pretty common. In fact, if you think about stars, they're hot. Hot, hot gas. All gas, no liquid solid. Hot. Moving around, hitting each other. And the atoms are going to tend to gain or lose electrons. They tend to lose electrons, making them positive or negative ions. you lose an electron, you lost the negative, and so you have positive ion. In a big gas fluid flow of electrically charged stuff, that's really complex plasma physics. So anyway, just those simple terms. And we'll talk about how materials respond electrically. Now, first thing, subatomic bits. Well, what about those electrons? One electron, how much charge does it have? Well, you might guess, that's why we called it. It has the charge of an electron is equal to negative 1e, or negative, right? You've got that memorized right now. 1.6 times 10 to the negative 19. So that's a negative 1.6 times, and write it. Don't get stuck in your head. That's a mistake that people made for thousands of years. Right. A proton, it's interesting, has the same amount of electric charge, but of course it has an opposite action. And so again, it's positive 1.6 times 10 to the negative 19 coulombs. And you write it off. You don't have to think about it. Just keep writing it. Learn by doing it. So interesting, because the proton has about how much more mass? Remember that number, 1,800? Good old 1,800s for EM. So about 1,800 times more mass. Very massive, right? But it's got the same electric charge, except opposite effect, pull versus push. Why? Why does it have the same? We aren't going there. Let it go, Ben. Franklin. Let it go. You know, you got a lot more to learn. Do all the homework, run through the problems, do your circuits, then you'll be preparing yourself, but do the work. Now, interestingly, that protons, as I mentioned, are made up of 3 quarks, and neutrons are made of 3 quarks, and these aren't common. What's common is electrons, protons, and neutrons making up stuff, the air, etc. But there are 6 types of quarks, and it's kind of interesting. I just should note that the quarks can have plus 1/3 e, or minus 1/3 e, or plus 2/3 e, or minus 2/3 e. So they're interesting bits. All right. So we come over here, and I want to talk about 2 properties of electric charge, and then talk about materials. So number 1, it's quantized. It comes in set amounts. You know, so I can't have, if I have half a pen, I have a mess. So I got 1 pen, I got 2 pens, I got 3 pens, or pennies, or dollar bills. So they come in units. That's all quantized means. You can't have half of it. So generally, integer multiples of 1e. Now I know the quarks are weird, so whatever. So you can have negative 27e. You can have positive 2 point. Look at that. Wait, there's a fraction. Oh no. Oh no, he didn't do that. You can't have a fraction of e, but if I multiply times 10 to the 3, then that's an integer number, right? Or 10 to the 13, that's an integer number. So realize that. So that's just the rule of the game. And it's also conserved. So that means I can lose my keys, right? Oh, I lost my keys, but I can't lose electric charge. I can lose electric charge, but someone's going to get it, right? And I suppose my keys too. If I lose my keys, my drawer found it or something. But it's always somewhere, right? Your keys are always somewhere. You can hope that's true. So conserved. One object loses, another gains. Usually, again, keep in mind, we are talking about electron transfer, certainly at the beginning of the game until you get to some other stuff. So that's all. So ion charge, an atom, if it's lost 2 electrons, then it has plus 2e charge. If it's gained 3 electrons from being neutral, then it has negative 3e of charge. I'll put it in coulombs. If it's lost 11 electrons, then it's positive 11e of charge. That's all. So atoms can lose, but someone had to get them. So let's talk about materials over here, and so this gets kind of interesting down here. So material types. Now materials come in a wide range. As you might know, say from friction, there's different roughnesses of surface, a whole range of roughness. It's a whole range of materials. and conditions. But generally, when we talk about a conductor, we're saying that conductors allow free electrons to move around or flow from one end to another. In metals, this is a fun topic, there are 1 to 4 free electrons. The other ones are stuck in close to the nucleus, but there's 1 to 4 free electrons in metal atoms. And they're just like, they're whatever, they just go where they please, right? And they're allowed to flow. Insulators or non-conductors, it's hard to get the electrons to go from one atom to another. You can get it, but it's much harder. So like wood, it's not going to conduct electricity well. Gold is great, copper, right, etc. Silver. Semiconductors, you can guess, it's in between, right? And so, interesting property is there. To be explored this introduction slide. So what if we bring a charged object near a neutral object? So these are good, interesting cases to notice. If I take a positive object, what does that mean? If it's positive, have I added protons? This is important. Have I added protons? I mean, that's a nuclear reaction. Right. When people draw these plus, they don't mean there's extra protons. That means there's a lack of electrons, right? It's a lack of electrons. The protons are stuck in the nucleus. That's the next semester, right? Now, how do I get that? Oh, let me just remember this. How did I do that? I did fur, rubber. And I did it in this order, so the electrons go over here. So this became negative, that became positive. So if I want a positive, I could use fur, or I could use glass. The S goes to silk. Electrons go that way. Again, this became positive. So I could take a glass rod that's rubbed with silk, move it near a conductor or an insulator. Here, I can take fur, rubber with rubber, and the rubber has gained electrons. So when you see this picture, realize that's extra electrons, mostly. I know there's other situations. And that's a lack of electrons because of the rubbing, good old Ben Franklin, and good old Electra and Amber. What happens in the conductor? Well, again, atoms are made of electrons and protons and neutrons. The protons and neutrons don't move around. Not across the thing. In a conductor, electrons will see will they be attracted or repulsed? Here's a lack of electrons. And you've got some free electrons here. Lack electrons. This is positive. Do electrons attract or are they repulsed? Are opposites attracted? Yeah, so I'm going to draw them like this, even though in reality I'm talking about extra electrons. This is an important idea. Now that leaves, where'd they come from? Well, they had to migrate over there a little bit, all the way across through the conductor, leaving a positive side, not protons, but this is a lack of electrons. Now we say that the object is polarized. Polar, North Pole, South Pole. It's two different sides, opposite sides. So the object is polarized. What if I bring the negative towards it? What do the electrons do? They say, I'm out of here. I do not like you guys. They don't like each other either. So they got, eventually they don't go over there anymore. It's like, I don't like you, I don't like you. They just don't like each other. But they do get away from that if they have to, leaving, again, a lack electrons, extra electrons, extra electrons. So think of those pictures when they draw them like that. If they show positives moving up, there's no protons moving up. Electrons are generally moving down, unless it's some other special case. So we say that here that the object is polarized by free electron movement, or buildup, if you will. What happens if I bring it near an insulator? This is interesting, and leads to some curious things we're not going to get to right now. Within the atom, the electron doesn't leave the atom, but the electrons do like the plus. So within the atom, and of course I'll exaggerate this, the electrons lean this way, and the nucleus leans this way. The protons of the atom are not attracted, they're repulsed. Again, the electrons are attracted, the protons are repulsed, and so the atom, we say the atom is polarized. As opposed to the object. And then you could figure out what would happen down there too, right? Still, the atom is polarized. But now, the electrons say, no, I want to get out of here. Leaving the nucleus there, and they lean a little bit, right? Attraction, repulsion. And that slight difference will give us some interesting results we see. So again, the atom is polarized here in an insulator, whereas the object is polarized here with a conductor, just from this simple case. And we can use that a ton to engineer all kinds of really cool stuff. Capacitors, often metal, are you take electrons from one side, move to the other, maybe with a battery.